Welcome to this webinar presented by the IET's Anglian Coastal Local Network, which represents members in Norfolk and Suffolk. Welcome also to folks from other parts of the UK and indeed globally. I'm delighted to welcome you all. I'm Kevin Foster and I'm Chairman of the Anglian Coastal IET Local Network, and I will be your host for this evening. Now, we will leave questions until the end of the presentation, please. So if you think of a question, use the Q&A panel in Zoom and not the chat, please. Now, if you wiggle your mouse near the bottom of your screen, you will see it on the Zoom taskbar, and you can select chat or Q&A. So please use the Q&A button for questions, please. The webinar will be recorded and we will try and get through as many of the questions as possible. So without further ado, I'm delighted to introduce John Halleur, MBE. John is a retired senior manager who spent his career at the leading edge of developing and supporting software solutions in the challenging environment of global telecommunications. John worked for BT for over 30 years, leading software engineering research and development related to new telephone exchanges, network management systems, software architectures, and latterly leading BT's UK network strategy unit. He retired from BT in 2000. In 1995, he was appointed non-executive director of the Indian BT joint venture called Mahindra BT. Then he became its COO in 2000 and CEO between 2001 and 2004, positioning it for its public flotation as Tech Mahindra. John is very interested in children's education and has previously been a school governor at primary and secondary level for over 40 years. He continues to help with maths mentoring, and in order to tackle embedded low literacy in disadvantaged areas of Ipswich, he has set up 2 local charities. John is a strong advocate of carbon reduction and is rapidly changing his lifestyle appropriately. Apart from his family, his main interest is music, playing in a woodwind quintet and a saxophone quartet. So John, it's over to you now.
Good evening, everybody. Thanks, Kevin. I'll just get my first slide up. So as Kevin said, my background is software engineering. I just want to stress I'm not part of the building industry. I'm just a one-off amateur self-builder. So I'm talking about a house that we built between 2011 and 2012. My wife and I did about 90% of the design, and then I project managed the build with a number of subcontractors. So this is about primarily feedback from my experiences. And I've reinforced that slightly with some research from the internet, but it's not deep research. So treat most of these figures as indicative only. There's going to be quite a lot of bullet points initially, but there'll be a respite in the middle with some pictures of the build, which I thought you might be interested in. And we'll have an exciting bit of poll in the middle as well. I offered to do this talk when about a year ago, we had a talk about passive house in Ipswich, and I thought it would be interesting to do the comparison between my case study new build and this passive house. And I want to cover 4 questions, really. So can a fairly ordinary looking house meet the passive house spec? Do the current rules and engineering norms that deliver passive house targets generally? Are these targets enough to save the planet? And what are we doing as engineers and individuals about that ourselves? So I'm going to cover those 4 areas. First off, the passive house. So what did we learn a year ago? We learned that primarily it was about the space heating demand. And we were told very clearly that the passive house target was 15 kilowatt hours per square meter per year. And we were looking at walls with a thermal transmission coefficient, so the amount of heat that leaks through them, coefficient for that of 0.15 for walls and roof and 0.8 for windows. And it also is based on a sealed building, so it requires mechanically ventilated with heat recovery, so ventilation with heat recovery. And the air movement has to be really well controlled with something like 1 cubic meter per hour per square meter of floor space. That's the basis. How does my practical example match up to that? So just an outline of the case study. So this is a build in central Ipswich. It was a constrained site with mature trees. It was deliberately designed primarily to cope with 2 people getting elderly gradually. So although it's got 3 bedrooms, the main bedroom is on the ground floor, and it was intended to be eco-friendly in both build and operation. And because I wanted to do the build fairly quickly, it was based on fairly standard size components, fairly standard components. So can that match passive house? So here's a picture of the front and the back of the house. It's about 168 square meters. We purchase every year about 3.65 megawatt hours of energy from any source. And that's about 21.7 kilowatt hours per square meter. And the mechanism that we use for walls and roof had this thermal factor of 0.17. The triple glazed doors and windows had a thermal factor of 0.93. And we sealed every joint that we could possibly find in the house and ended up with an air leakage figure of 2.84 cubic meters per hour per square meter. So lots of figures there. How does that actually compare with the passive house spec? So the components of walls and roof and the windows fairly close, but not quite close enough. Air tightness, definitely not. So although we tried very hard, the house is more leaky than one would hope to get with a passive house. And at face value, the annual heating demand looks as though it's not there, but we just need to go back and check, don't we? Because that passive house spec was about space heating only. And I've quoted so far the total, which includes lighting and cooking, washing machines and fridge, freezers and so on, and also the mechanical ventilation. So based on usage through the summer, so when there's no heating at all, the energy demand per day from the house is about 3 kilowatts to 5 kilowatt hours a day. So multiplying that up crudely, we would get about 1.46 megawatt hours per annum. So if we now apply that again to our square meterage, we would end up with a total demand just for the space heating of about 2.2 megawatt hours per annum and an overall space heating per square meter of 13.1. So maybe we've got there. I just wave a small flag that this is based on 2 people using the house, so that might not be quite a fair comparison, but let's just say we're pretty close. Just wanted to mention one other thing here, that the the internet tells me that the average house nowadays in the UK has a square meter floor space of between 70 and 80 square meters. So it's about half the size of this case study house at 168. And the average house uses 12 megawatt hours of gas and about 3.7 megawatt hours of electricity. So a total of about 15.7 compared to what we're talking about here, which is 3.6. So we're looking at something with twice the floor space and something like a quarter of the energy demand. So not too bad. So for the first question, it looks as though we could put this together and match passive house, but it looks as though we need active elements involved, not just passive elements. But I want to just raise one thing. So we're talking about operational energy, as I would call it. We're not talking about the energy required to do the build of the house. And I think we should look at that too. I don't know whether that's normally involved in the passive house spec, but I think we should address it. So it's called embodied energy or embodied carbon. And it's about the energy required to extract, refine, process, transport, and fabricate the materials of the house. The internet tells me it's typically 20 to 50% of the whole life energy of the building. So it's non-trivial, but often it's forgotten. So what should we be building with? So I've used a reference from David Mackay, which I've quoted down the bottom here, which is sustainable energy without the hot air, which I think you should read if you're interested in any of this stuff. It may be slightly older now, so it was very appropriate in 2011 or so when I was doing this. So here's a table largely pinched from that reference about different materials for building. You'll see from the central column that that's quoting kilowatt hours per kilogram. And that column itself tells you something about some of the materials to avoid. But I would just warn that you need to think about the weight of the materials going into a house. So if you take the top line of kiln dried sawn softwood and compare it to clay bricks, for instance, it looks as though the clay bricks might be a better bet. But if you actually apply the weight difference, then the kiln dried sawn wood is 80% less in terms of embodied energy than brick. And you can also see that if you look at things like the insulation at the bottom, comparing the fiberglass with hemp, you can see that there's quite a substantial difference. So embodied energy, let's look at what we actually used in our build then based on those figures. The main structure, so insulation and walls and roof, we used panels made of softwood with hemp insulation in them, which was about 370 millimeters width, which is what's recommended these days. The main construction was wood. It happened to have been oak frame that we used because we liked the idea of that, but you could use cheaper wood to do the framing. And we used softwood and fiberboard panels for the walls and the roof. And you could basically make the whole build out of those panels by just screwing them together. The alternative for the oak frame would be glue laminated wood. So we put lime render on the outside of that, which is more eco-friendly than any other type of render, and we also used oak weatherboarding. And the roof, we decided to use wooden shingles, so cedar shingles, instead of normal clay tiles. They probably haven't got quite the same lifespan, but they'll last for at least 60 years or so. All the windows and doors are oak framed with triple glazing, and that's filled with argon. And then we use steel guttering and downpipes because that's more environmentally friendly than plastic kit. So that was the main construction. We then added active components, so ground source heat pump, photovoltaic panels, solar thermal, the mechanically ventilated heat recovery system, and each room has got separate room stats to control timing and temperature. And then there was a bunch of other stuff where we used all LED lighting, so 60 LED lights. We've got a 3,000 litre underground rainwater store, which feeds 2 toilets and the garden tap. I'll mention it again later, but that with modern taps and so on has allowed us to save 50% of the water that we used to use in our old Victorian house. We designed to have south-facing windows where possible into the main living rooms to get solar gain. We don't have things like a tumble dryer because that uses too much energy. We don't have any gas, so we deliberately didn't connect any gas to the property, and we use a cooker with an induction hob, which seems to me to be extremely efficient. We also minimized waste, so we only used as much materials as we needed to. I was really careful about trying to estimate everything. And I tried really hard to minimize the bricks, the concrete, and the ironwork, although I don't think I succeeded as much as I would have liked. So how does that fit together now in terms of the overall embodied energy if we put those components into the build? So again, this is a pretty crude comparison, so don't get too excited about the accuracy of the numbers. So I used again the Mackay source to give me the basic information. So that's where the standard house information came from. So it's based on a standard house of 100 square meters floor space. And it's based on the usual brick and concrete tile or whatever brick tile construction. So the standard house in this example with 100 square meters of floor space comes out with an overall embodied energy of 42 1,000 kilowatt hours. I've just then approximated putting the materials I used into that same calculation, and it comes out at approximately 24 megawatt hours. It's close-ish to half. So just being a little bit more accurate than that, it's 58% of the standard British house. If you multiply that up from the 100 square meters to 168 square meters, the reality, then the embodied energy of my house is somewhere in the region of 41 megawatt hours. So you can then obviously compare that embodied energy, the cost of the building in energy terms, with the operational costs. And in terms of the numbers I've given you, it's about 11 years worth for the build. And if we built with standard components, it would have been something more like 19 years worth of operation in order to save that. So embodied energy, not to be forgotten, but often underestimated. So let's look at the active components, shall we? They might be the most fun stuff. So PV panels, the obvious thing to stick on the roof. We put 10 panels in. In those days, they were 250 watt peak panels. They're still performing pretty well after 8.5 years or so. They're probably running at about 95% of spec, and they generate 2.1 megawatt hours per annum. I noticed, and I'll talk about it again later, that the latest panels are coming out at about 370 watts, I think, a panel, or 400 maybe, and that would allow me to get 3.3 megawatt hours out of the same roof space. The solar thermals, 20 vacuum tubes, my guess is it's about 240 kilowatts per annum worth to me. I might well have been better off putting 1 or 2 additional PV panels in there instead, but the ground source heat pump, it's a 6 kilowatt Kenza, manufactured in Cornwall. Nominally, it has about a 4-to-1 gain. So for every kilowatt hour of electricity you put into it, it generates 3 or 4 kilowatt hours of heat. So it's extremely efficient. I think they cost about £5,000 to buy the box these days. And then there's another amount of money, which I'm guessing is in the £4,000 to £5,000 mark. It might be more, to put a collector in the ground. So that can either be a slinky that goes in into a trench, which is, I don't know, about 5 or 6 feet deep, or it can be vertically drilled bores in the ground. In my case, we've got 120 meters of collector. It's in 4 vertical 30-meter bores because there wasn't enough room for the slinky. I should say that the heat pump is extremely low maintenance, so there's hardly any maintenance needed. That drives an underfloor heating system with water circulating, and basically there's 1 or more loops in each room. So I'm then able to control each loop independently with a timer and thermostat. So basically we run each room at a different temperature, potentially in a range of about 18 degrees to 22 or something like that. So we can be very efficient with using the heat. You just have to remember with a ground source heat pump that you need to treat it a bit like always on data, that it doesn't heat up very quickly, so you have to have it on more than you would expect. So the mechanically ventilated is just simply a couple of fans sitting in a box. One fan extracts the stale warm air from places like bathrooms and kitchens, and the other fan brings fresh air in and puts them into the living rooms, puts that separately into the living rooms. And in the box, there's a heat exchanger that moves the heat from the exhaust air into the incoming fresh air. So it's normally 90% efficient. So you lose very little heat, whereas with drafts in a normal house, you lose an immense amount of your energy through the drafts that you have. So LED lighting, we've had experience of massive amount of these, so 27 downlighters. I chose to use GU10 spot bulbs in GU10 holders, which I could adjust because I wasn't sure how to do the lighting design. And that seems to have turned out pretty well, really. I think we've had about 2 or 3 failures of those in the 8.5 years. They've been pretty reliable, not necessarily up to their spec of reliability, but pretty darn good. So overall, there's nothing very clever there when you boil it down. It's mostly pumps and fans. So what's supposedly futuristic is pretty basic, actually, in plumbing terms or whatever. I should say there's obviously embedded energy in those active components, which I haven't calculated. So there's actually more energy cost with them. I thought you might like to see something about the money. So this is from my personal experience. So it might not be in any way typical. The operational savings. So we were in a Victorian house, which was similar sort of floor space in the end, but leaked like a sieve in terms of drafts, etc. So we made quite a lot of savings on water because we were only using half the water now. That's quite valuable, really. No boiler maintenance, basically. So operational savings in the 8 years or so has been nearly 8,000. And then there are incentive payments for the various active components. So there's the renewable heat incentive for the ground source heat pump and the solar thermal, and then feed-in tariff for the photovoltaic. Now, I put those in and got those incentives when they were at their best. I think you can still get the ground source heat pump RHI, so that one would still be valid. So overall, the efficiency gains has paid me back quite a lot in the 8.5 years. I looked on the internet to get sort of current state of play in terms of return on investment and payback period, which I put at the bottom here. So the internet tells me, and again, be skeptical about these numbers, so they might not be right, but I suspect they're in the right sort of order. Ground source heat pump with a payback period of 11 to 12 years, and the photovoltaics with a payback of about 16 years now. The payback for me with the incentives I got was more like 10 years, I think. So anybody with money in the bank, sitting in the bank with zero interest, should be thinking about investing in active renewable components, because you'll get a better return on that money that you've got. So I thought you'd like a rest from the bullet points at this stage. So I thought I'd show you some pictures of the actual build, since you're all engineers out there. Top picture, the crude red triangle, rectangle is an attempt to show you roughly where the site is of the build. It's sitting in the back garden of the Victorian house. And it used to be our vegetable patch. So you can see on the left-hand side, it was distinctly fallow before the build. And you might just like to note this 200-year-old copper beech tree, which is a major feature on the site and had to be protected. Quite fun in that we had to access the site, if you look at the right-hand picture, through a very narrow driveway with about 2 or 3 inches on either side for the major tractors and things like that coming up and down. And we had to feed the site from a pretty small urban road, really. So it was an interesting exercise. So the good old tree imposed lots of challenges on the foundations. So the root protection zone for this tree covered about 1/3 of the site, and it was the third where it made most sense to put the house. So we ended up needing to put the house on piles rather than strip foundations. And engineering told me it was 24 piles, which had to be 6 meters deep. So they are 300 millimeters in diameter, these piles, reinforced, and they're 6 meters deep. And if you look at the left-hand side, some poor devil had to use an air lance to blow the air out from the top of each pile hole to check that there were no major roots in there that would be damaged by piling. A young worker had to do that for 24 piles, poor chap. I gave him lots of moral support. This is the picture of the guys drilling. On the top right-hand side, you can see piles exposed by the digging out of a cellar, which is basically the basis for an equipment room. And below that, on the bottom right-hand side, you can see it massively reinforced to make sure it doesn't disappear anywhere, I suppose. The engineers amongst you will enjoy the fact that you can see that we plan to put plenty of ducting in for all the services leading into the equipment room. And I thought you might like to notice that bottom middle, we had to get an archaeologist guy in to check that we weren't putting the cellar in the middle of any sort of Saxon site. Foundations, lots of concrete and rebar going in. You can see the cellar has appeared as a nice brick bunker, concrete bunker now, which is 3 meters by 4 meters by 2.4 meters high. And here's a lovely clean base. So it's a fairly massive concrete reinforced base sitting on 24 6-meter pillars. I think that's probably enough for about a 4-story office block or something. So the frame, this is preformed wooden Lego. This was manufactured in Hereford. In this case, it's oak, and it was designed on computer. Came as I say, preformed Lego bricks that were fitted together on site. You can imagine that we had quite fun getting the 40-ton crane down the limited access site, literally about an inch to spare on either side. Each piece gets craned into place, and then the guys basically get in and stick it in the joints and whack in wooden pins to hold it all together. And then this is oak, which dries out and clamps all the joints as it dries. So we put SIP panels in for roof and wall, so structurally insulated panels, so pre-insulated. As it says on here, there's a softwood frame and then wood fiber and OSB board on the outside skins, a hemp insulation, and then inner outer breather membranes. So you can see the 2 different types of membrane on here. And those, again, computer designed and basically just get whacked straight on, screwed onto the frame. Or, as I said earlier on, you can just screw these SIPs together to make the house on its own without the frame. It forms its own frame if required. So you just need sort of foot-long screws to go in. You might be interested in the fact that we were using these lightweight posi joists up on the right-hand side here, which are really good for running services down the middle of the ceiling void. The last one is for all the plumbers amongst you. So this is our cellar equipment room now with the kit in it. Left-hand side, you can see the white box is the ground source heat pump. It looks like a mid-sized fridge. It sounds like a mid-sized fridge. And it basically behaves like a mid-sized fridge working in reverse. I've shown you here what the latest version looks like, and they call that the shoebox. So that's also a 6 kilowatt ground source heat pump, but can now fit in somebody's cupboard. The white blobs are expansion tanks to deal with pressure changes. The upper middle picture is the PV inverter for the solar panels on the roof. This one is Solar Edge. Relatively recently, I had the panels relinked in parallel. They were originally in series, and that's less efficient than having them linked by Solar Edge in a parallel format. And then the right-hand side is the solar thermal stuff, with the grey bit is basically just a pump to pump the very hot water from the roof round into this big 6-foot tank, or thermal store as they like to call it these days. So I'm afraid that's all the pictures I've got time for at the moment. So I want to now raise the engineering issues I came up against during this build. What's happening is the building industry seemed, certainly at that time, and I suspect it still is when I look at building sites, it's still clinging on to old methods and components. It's still not worrying about the embodied energy of what it's using to make the builds. And there seems to be little understanding at any level from architects onwards, it seemed to me, certainly with my experience anyway, of what's needed with a green approach. So I certainly ended up fighting at every level to make sure that green solutions and new techniques were put in. I should stress that the approach of SIP panels and so on, I think will work extremely well and is very amenable to factory production. So it's much more rapid on site. You don't get loads of problems with water, etc. It's a quicker and drier solution. I'm sure in Germany and places they actually have services already installed in those SIP panels, so you can just plug wiring, etc. together. I was told by my contractors that there's massive amounts of waste on sites generally, all of which is costing energy. I came across several examples of overestimation. Had a substantial problem with the heating design where they were trying to get me to buy a ground source heat pump which was twice the size as it needed. I ended up having to do my own spreadsheet and worked out that in worst case I needed about 2 kilowatt hours per hour to heat the whole house under really cold conditions. So the 6 kilowatt ground source heat pump is actually overkill, really. And I still think maybe those foundations were a bit over engineered. I'm sure the engineering company I used did all the right things, did the right algorithm and so on, but I would question whether that's appropriate with a lightweight house. So it was a lightweight wooden house sitting on 24 pillars. You would think that that wouldn't require a massive base, but there you go. I think the bit that got to me most was the fact that to get planning permission, you have to, well, at the time I had to fill in a code for sustainable homes, which was a point system to encourage sustainable buildings, apparently. I had to get an engineering performance certificate done, which was a spreadsheet assessing the operational energy of the building. So it was interesting because I wonder what you think the answers would come out for with this house. So we've just seen that it's very close to passive house, maybe slightly better even. So that's the operational energy bit is good. You saw that the embodied energy bit was pretty good, and you can take it from me that I was very careful with the build. Where did we come out in terms of the code for sustainable homes, which is a range, it goes up to 100, and the pass mark for planners is 60. So here's what we got. So we just passed. We didn't get highly efficient on the engineering performance certificate either, energy performance certificate either, which is, I was fairly incandescent when that happened. I decided I'd look. So I went through very carefully the code for sustainable homes. So this was in 2012 now. And what I found was it was very biased towards site management points and biased away from embodied energy and operational energy points, which seemed to me to be the opposite of achieving a sustainable home. It was also radically biased against self-builders. You couldn't sign up to their considerate constructors scheme or lifetime home schemes or waste management scheme. Even though you followed all the principles, you couldn't get any points for that as a self-builder. For the spreadsheet bit, I in the end, I unpicked the spreadsheet step by step and discovered that it was biased against new technologies. So it totally omitted LED lighting. And the one I liked most was that you got more points for an efficient gas boiler at 90% than you did for a ground source heat pump at 40% efficient. So I found that slightly confusing. And overall, I discovered an error level of about 30% in the spreadsheet. I don't think I've got time to go into that really, but there are other government figures for PV generation which are better than and different from the ones they use in the spreadsheet for reasons I didn't understand, and they were certainly worse than the reality that I was seeing on the ground. And as we said, they didn't include LEDs, and there was a thermal bridging, so this was losses around the windows, etc., and door handles and things, where if nobody seems to know what real thermal bridging coefficients are, so you end up using a default in the system which is horrendous and it's really draconian. The bit that I think irritated me the most was that they calculated the nitrous oxide and the carbon levels for grid electricity generation from figures that were from, I think, 2008, maybe 2010, not 2012 when I built the house. And my point would be, why isn't it a half-life of the house? So if you expect the house to last for 60 years, surely you should take the predicted electricity generation figures for carbon and NOx at 30 years hence. So I'll just show you what's happened to those grid carbon mix over the last few years. And I got this from a source called Carbon Brief, which I think is acceptable. It was the best I could find in terms of display. So I just explain the key colors to you, so you can ignore some of the colors, but the key ones are: black is the coal, blue is gas, the brown one is nuclear, the yellow is renewables, and the purpley one is called imports, which I guess must be gas as well, I don't know. We obviously did the build in 2012. I think the assessment in the spreadsheets was in 2010 or something, which was horrendous. So it was a largely mixed, massively coal and gas. So fossil fuel components, then, if I've just used these figures approximately from the graph, it's about 80% then. Now it will be about 45%. And if you predict forward to just 2035, so not even a 30-year forward prediction, it will be at least down below 25%. Based on what the Prime Minister is saying, it should well be lower than that. So massively different. Basically, I was so incensed by that that I contacted the building's research establishment, and I sent them my analysis of their code and their spreadsheet. And I also sent them a report with several recommendations. I don't know what happened to that, but I think the code for sustainable homes has been stopped, and I don't know what's replaced it. But I also know the EPC is still spreadsheet based, and I don't know what's in that anymore. So if you're interested, you may have to just unpick those yourselves. Moving towards a conclusion, we've looked at the embodied energy as being important and the operational energy, but we've also struggled to understand that the industry is struggling and loath to take on new approaches and green techniques. They have to do it. We just have to make these changes. So these standards, they ought to be forward thinking, not lagging. I don't understand why that isn't right. We're a profession. We should be getting these things right. Let's talk about what we're doing now ourselves. And I thought we might just start with a quick poll. So we're going to allow a minute or so for you to fill in the poll. Let's look at where we are with targets for each household then. Having looked at the house itself, let's look at the household. So I used a calculator, which I've indicated here. I don't know whether it's the best. It seems to be pretty good. And using the case study, so my household with our current lifestyle, we came out with 3.77 tons of carbon per annum. So where does that fit? So UK average is 14.1 and the USA is 17.6 apparently. Other parts of the world are lower, but I'm guessing that they're looking to even upwards. The key thing that we all need to look at is where do we need to be? And I think the target for 2050 is somewhere around 2 to 3 tons per household per annum. I got that from the SGR reference, but I couldn't find an up-to-date one I felt really comfortable with. So it's somewhere in that range, I think. It may be getting worse or reducing with time. Basically, what you can see is I'm not there yet. So I've done all these other things, but I'm not there yet. So is there anything more I could do? Well, I can improve the house. So I could be replacing the PV panels to get more generation. That would cover quite a substantial difference for me. I could use battery storage to make sure I actually use what I generate in the house rather than exporting it and then buying something back in. And that would give me grid resilience. I could, in theory, use the car batteries. So I'm going to talk about the electric car in a minute, but we could use the car batteries, and it is feasible to have a two-way charger, which would allow me to run the house off the car batteries. So that's the optimum for me, I think, is doing that, which would get me pretty close to zero carbon and quickly. So my wife and I are changing our culture. These are the things we're doing and we would suggest you all think about. None of it's very clever, and it is possible. We are reducing our plastic use. We are radically reducing our meat usage. We have just got an electric car. 2 big ones at the end, really. Don't buy so much stuff. Don't waste so much stuff. One of the things I do is each January, I look at the rough carbon footprint for the household over the year, and then I do an offsetting donation to the Woodland Trust to plant trees. That's my backstop to catch anything that I've not, any carbon that I've generated otherwise. So George Williamson was quite keen that I should tell you about the car briefly. I think I've got a couple of minutes to do that. So had it for 4 months now, about 1,200 miles of usage. It's a Kia e-Niro. It's a 5-door sort of mid-sized MPV. For the petrol heads, it's 200 brake horsepower. And I'm told, I haven't done it yet, but it does 0 to 60 in 6.9 seconds. So it's a bit better than a wind-up car, really. It does a genuine 280 miles of range with a 64 kilowatt battery. It's been doing better than that range in the summer. I guess it will do worse than that in the winter, but it's pretty good. It's very efficient around town. It's reasonably efficient on motorways. I'm charging it at home with a My Energy Zappy charger, which is a British made charger. It does 7 kilowatts from the grid. And what I like about it is it gives me an option to do a PV trickle charge straight from the PV panels. So it will only take the PV, which obviously costs me nothing to fuel the car at that rate. So at the moment, it's costing me between 1p and 4p a mile to run. If I use fast chargers on motorways or whatever, it costs about 6 or 7p a mile. And it really is excellent to drive. It's got excellent acceleration. It works very well in slow traffic in towns. It's very quiet and it goes up hills like a bomb. Should you get one or not, there is a penalty in terms of embodied energy in the car, apparently, certainly at this stage. So it takes slightly more carbon to build an electric car, so the IET journal tells me, but you can recover that over the mileage that you use the car. And the Boundless journal told me that the EV lifetime emissions is lower, quite substantially lower than a petrol car. So you have to judge when you jump, or if you jump. Just to round off then, I think I've suggested that it can be pretty easy and fast to build close to passive house without it being extraordinarily expensive. Active components can get you to passive house or better. We should remember that we need to worry about the materials we use and the embodied energy. And for goodness sake, guys, let's sort out the engineering standards, because my suspicion is, although they might not be as bad as they were in 2012, they are not good enough for getting us to 2050. And we'll see what the poll was saying, but I suspect we all need to do lots as individuals and engineers. And we need to do that starting now, not waiting for 2030 or 2050. That's it. Thank you very much.
Thanks very much, John, for a fascinating presentation. What are we going to do now is I'm going to hand over to my colleague George Williamson, who's going to manage the Q&A. And I see there are about 29 questions, so I think we should just crack on with the Q&A. So over to you, George.
Question. Are the energy use numbers primary energy, i.e. is electricity use corrected for generating and transmission losses?
I honestly don't know that. I think they're useful as a comparator, but I don't know what is actually in them. I found it quite difficult to get solid numbers out of the internet, I have to say, on several of those aspects. I wasn't entirely sure how good they were, which is why I was stressing that it's indicative. You may have to find better sources.
Okay, John, question from Simon Eddleston, who thanks you for the presentation. From the embodied carbon calculation, what duration is considered to be the whole life of the building?
Well, I guess it depends on its construction, but I think your guess is as good as mine. I'm reckoning that if my house doesn't last for 60 years, I'll be amazed. So I just give Simon an example. If you think oak frame and wooden paneling is somewhat dodgy life-wise, I would suggest you go to Lavenham in Suffolk and you'll see houses that were built about 500 or 600 years ago, still there and perfectly usable. So I don't know the answer to the question. I don't know if there's a norm that the engineering organizations use, or BRE, but certainly with the technology I've used, I would expect my house to be here in at least 100 years.
Okay, John, a question from Malcolm. How many kilowatt hours of solar photovoltaic did you use? And do you find that this makes up for the lack of gas, or are you buying a lot from the grid?
Okay, so I think I tried to cover that before. So we generate 2.1 megawatt hours per annum from the PV panels, and the assumption from government, so I'm not able to measure what I use and what I export to the grid. The government figures assume half of it goes to the grid and half of it is used in the house. My suspicion is that because we generate most of the energy during the day, obviously when there's sun, but we use most of our energy in the evenings when it's cold and dark, that I suspect it's more like a third of that generated energy is used in the house and about 2/3 is exported. You have to factor that calculation in, but then we literally buy 3.6 megawatt hours per annum of electricity. We don't have any other source of energy. So we buy 3.6, we generate 2.1. Can I just add to that, George? If you look at what I was saying about putting better panels on, I could use currently best practice panels and generate another 1.2 megawatt hours per annum, I think, which would take another chunk out of what I buy.
John, question from John Pelmore. Do you use a large storage tank for the heating?
There's 2 storage tanks. So there's one large one for hot water, for usage as hot water, but there's also a smaller one which is for the underfloor heating. So basically you have a tank there of hot water ready if you want to switch the underfloor heating on, so you're not starting from zero. And I can't tell you the capacities of those 2, but hot water thermal store is about 6 foot by 1'6" radius or something, cylinder. And the other one is about half that size.
Question, John, from it's about ventilation, from Roger Castle-Smith. Doesn't a sealed building stand to create a very stuffy atmosphere? Are there issues with cooking smells?
It would be very stuffy if you didn't have the ventilation. So you can't seal a building and not have mechanically ventilated ventilation, and you would get horrible condensation problems. If you put the MVHR in, it's absolutely fine. So if you can imagine, you've got a constant airflow, and the constant airflow is gently taking the stale air from kitchens and bathrooms, etc. The air is moving from the places like sitting rooms into the kitchen or the bathroom and then away. All the smells disappear, and you're basically breathing fresh air all the time. But it's not cold fresh air, it's warmed from the warmth in the stale exhaust air. So it's really good. It's quite it would be difficult to retrofit into an existing building, because you need air ducts. You need 2 lots of air ducts, one set of air ducts bringing the air into the living rooms, and one set of air ducts taking stale air away from bathrooms and kitchens.
John, question from Ian Collins. Does the low thermal mass and south-facing glazing lead to overheating in summer, and how do you deal with it?
It could do easily. If you notice from the pictures at the beginning, we don't have massive windows. It's not like many of the grand designs type buildings that you see where have a massive amount of glass. The simple answer is that you close the curtains. So you do in extreme cases need screening of some kind.
Question from Simon Elston. What temperature does the solar thermal hot water system operate at, and does it need significant electric heating backup? I'm
not sure what temperature it operates at, but it's extremely hot. So the pipes are extremely well insulated to protect people from the heat from the solar thermal. My guess is it gets very close to boiling point. Do you need electrical backup? We obviously do need backup, because like today, there's been no sunshine at all today to give you any of the solar thermal gain for your hot water. But we can heat the hot water from the ground source heat pump. So our primary fallback is the ground source heat pump operating at 3 or 4 to 1. So if we need a couple, 2 or 3 kilowatt hours of energy to go into the hot water, we're probably only using 1 kilowatt hour of energy going into the ground source heat pump.
And a supplementary, did you consider using battery with the PV panels?
I am considering using battery with the PV panels. It's quite expensive to buy separate batteries to go in. So I think I'd be quite keen to be able to run the house for something like a day on batteries, which would, in worst case conditions, would require me to store about 30 kilowatt hours. And that would be quite expensive. What I'm really keen on is using the 64 kilowatt hour battery in the car. If I can have this 2-way charger working, and I'm told by my energy that they're working on it, my car would give me 2 days worth of operation of the house under the coldest conditions, which would be pretty good, really, wouldn't it?
John, question from Mike Roper. He agrees with your EPC methodology, recognises it's a simple standardised assessment. Mike lives in a 1990 pot and timber frame house, similar in construction to yours, and EPC assumes solid concrete floors. They're insulated suspended floors. So that's really a supplementary answer from Mike for you there.
Yeah, thanks, Mike. I mean, why this is still, I'm guessing it isn't perfect yet by any means, the EPC. I think frankly, as a professional engineer, I think there's no excuse for it not being right. And I would argue that I gave them suggestions on how to get that right back in 2014 or something. It isn't mind-blowing to get this right. It's not a substantially difficult thing to do. You just have to have a menu of components for floors or walls or whatever with the right parameters attached to them and plug them in. Really simple.
Alan Ferdman's asked a question, thanking you for interesting talk and asking if there's any chance of seeing the layout of rooms, sizes, etc.
I don't see why not, if we can find a way of passing stuff to people.
We would normally put the slides up on the IET site, so if you can add some floor plans, that would answer that question, John. From Dave Baker, how does total build cost compare with a conventional build?
I struggle to answer that one because we were building our own house to live in forever. As I say, we use things like oak frame, which is obviously much more expensive than it needs to be. If you like, we wasted money on certain things. So our specific house is probably fairly expensive, but you can build with those SIP panels, and you could build an equally eco-friendly house for a very substantially less amount of money using the methods that you basically saw there. So as I said before, you can do it without any substantial frame at all. And I think there are companies that do it. And I think if you went to the States, you would see most of the houses built that way. I think in lots of parts of Europe, you would find houses built that way. We are way behind, and I don't know why. It's pathetic, really. And you'd save money because it's faster to do. So you don't have lots of scaffolding and stuff hanging around costing you a fortune.
A point of clarification from David Learmont, obviously aware of the industry. He notes that CFSH has disappeared and our government has removed that as a consequence of lobbying from the house building industry.
Yeah, it was already geared up in their favour, so it wasn't actually achieving sustainable homes. It was very much about patting the industry on the back, I think, frankly. I don't know what's replaced it. There are apparently planning and whatever standards in its stead. I can't be bothered, frankly, to go and unpick them myself. But, as I say, I shared with BRE what I thought was wrong with the code and the EPC. And I shared how I thought it should be amended. I mean, the obvious thing is to prioritise operational energy and embodied energy, which was not the way it was built.
Question from Soma. I think the question about use of PV generated electricity you've already answered, but he wants to know what the operational strategy for using solar PV is in your mind. Operational strategy,
I'm not quite sure I understand that. I mean, from my perspective, my personal perspective as a house owner, over time, I want to screw as much electricity off the same roof space as possible. So if you technology guys can come up with PV panels that generate 500 watts each at a reasonable price, I would be very happy. And I think that would make my house pretty much totally energy self-sufficient. And I wouldn't need to do anything to the house, just replace the panels. So my strategy is to ultimately use the best practice panels as they improve to drive up the energy efficiency of the overall house. If you want to talk wider, I think every house in the country or every garage or every shop or wherever that, certainly where there's any site of a southeast or southwest facing roof, we should be putting panels on it. As I said, there's no point in keeping your money in the bank. You should be putting your money in PV panels.
Where's the best place to start if you're considering building or refitting an old house now? How would you find the right kind of sustainable builders, architects, installers?
I honestly find that difficult to answer because I tried to find an architect who was interested in green methods and approach, and I contacted the RBA, whatever it is, and I got a local architect who seemed keen on it, but ended up knowing very little, frankly. So I'm not sure how you get one that you can be sure of, other than to interview them strongly before you appoint them. Again, everybody knows about the problem of finding contractors to do things. I don't know whether there are approved ones that are eco-friendly approved. You could try the eco websites to see whether they've got approved suppliers or not. I'm happy to tell people where I found my materials from, but you end up hoping to God that you pick the right contractors, honestly. And then you have to sit on them to make sure they do the right things.
I've got a few supportive arguments from P. Gregory on the BRE calculations and from Simon Madison about the challenges of retrofitting older houses. So Simon's saying, what are your thoughts about retrofitting older and existing houses? Which things are straightforward, which things are more difficult?
Okay, it's utterly essential that we do that because the energy cost of the old houses is huge. Obviously, you start with the insulation in the loft. If you haven't got 370 millimeters in the loft, for goodness sake, do it, because it pays for itself in months rather than years. If you can insulate if you've got gaps in the walls and you can insulate that, that's good. You may have to use insulated plasterboard on something on the inside or insulated rendering type stuff on the outside. And I guess there's a whole range of potential draft proofing measures that you can use. Obviously, you can't afford to take that too far unless you put MVHR in, which is, as I said, I think that's pretty difficult to do generally. I think there are small scale ground source heat pumps and air source heat pumps that you could replace boilers with, but then you really need them operating with underfloor heating, I think, although you may be able to use them with panel radiators, but that's quite hard. So it is a challenge for sure. And obviously there are now, well, everything is potentially double glazed and triple glazed. I think you can get very thin double glazing if you've got Victorian houses and you're not allowed to put thick stuff in, but I would shy away from the plastic stuff. So I know it's difficult. I mean, it was much easier for me to do the new build than it was to improve my Victorian house. George, before we finish, can we just have a view on the poll? That's interesting. As I said before, invest in PV panels, don't leave your money in the bank. If you're going to do anything in your house, the loft insulation, etc., a decent depth like 370 is essential and very cheap and pays back within a year. So do it, please.
This one is about double, triple glazing. 87% have said yes, they already have it. 13% said no. And do they plan on doing it in the next 12 months? 24% said yes, and 76% said no.
We need to get rid of gas, guys. So I'm utterly amazed about how efficient the induction hob seems to be. The loss of external heat is extremely low with it. It's amazing. So it's creeping in then slowly. Yeah, that's a bit like money blowing out through the gaps in your floor or whatever. It's a huge loss.
10% do use one and 90% do not, but 20% said they would consider buying one in the next 12 months, but 80% would not.
Interesting. I mean, reducing is the good thing, though. Don't underestimate the impact on climate and energy costs of meat. It's huge. And if you're not sure, just look at the amount of forest that's being burnt down in Brazil in order to run cattle on that stuff. So we're actually throwing away the lungs of the planet in order to generate some beef. Thanks for the feedback, guys. That was great.
I'm afraid we don't have much time for further questions. I'll ask one more as a final question, John. Can the heat pump be used in reverse for cooling in summer?
It can, yes. So you end up with slightly cooler floors. And the good news about it is you're taking that heat and putting it back in the ground where it's stored, so you can use it again more easily. So the heat then comes back in the winter for you. I mean, I don't think it cools massively. It's not like air conditioning, but it helps.
I think we probably run out of time for questions. Apologies to those of you who have not had your questions answered. We'll see what we can do about that one offline. Thank you.
Okay, many thanks, George, and many thanks, John. John, thank you so much for a really fascinating and extremely thought-provoking presentation. It certainly made me think personally about my own carbon footprint, and I'll certainly try and take on board some of the tips that you've given as I embark on my next self-build project, which it's not so ambitious as yours, but it's one I've been thinking about. So I shall bear in mind your presentation. And I'm sure you've given us all really many ideas for the changes we can make to our own lives to give a more sustainable future. So with that, I'd like to remind all the listeners, we are recording the webinar and it will be available on the IET community's website as soon as possible. So next, I would like to draw your attention to our next confirmed webinar, which will be about indoor localization in the IoT era, and that will be on the 30th of November. And as you can see from the screen, we're finalizing dates for several others in November and December. So please check out our IET community website for details. So finally, on behalf of the IET Anglian Coastal Local Network, thank you all for joining tonight. And thank you all to the team who put tonight's webinar together and to John for a fantastic presentation. So that concludes the webinar tonight. You may disconnect now. Thank you.